Imagine the solar system, a mesmerizing cosmic ballet where planets, moons, and rings twirl around the sun in a seemingly perfect, flattened disk. From childhood, we're taught to picture this elegant arrangement. Planets orbiting in neat, concentric paths, all aligned on a single plane, moving in the same direction. It's a vision so familiar that we rarely pause to question it. But why is it this way? Is it a grand cosmic coincidence? Or did some ancient process sculpt this orderly structure? Spoiler alert, it's no coincidence. The universe, in its infinite complexity, has a knack for turning chaos into harmony, and the story of our solar system's flat orbital plane is a stunning example of this. Let's embark on a journey through time and space to uncover the how and why behind this phenomenon, a tale that spans billions of years, from the birth of stars to the formation of planets and moons. Buckle up, because this cosmic ride will captivate you until the very end. To understand why all the planets orbit the sun on the same plane, we need to rewind the clock to a time long before Earth existed, about 4.6 billion years ago. Picture a vast, swirling cloud of gas and dust, known as a molecular cloud or stellar nursery, floating in the depths of space. This cloud, primarily composed of hydrogen and helium with traces of heavier elements, was a chaotic mix of particles suspended in a delicate balance. Each particle resisted the gravitational pull of its neighbors, held apart by internal pressure, like a cosmic standoff. Then something extraordinary happened. An outside force, perhaps the shockwave from a nearby supernova, disrupted this equilibrium. The jolt caused particles to collide, clump together, and set off a chain reaction. These clumps grew, attracting more material, their mass and gravity increasing with each collision. Within a few thousand years, a dense, hot core began to form at the center of this collapsing cloud. A protostar, the embryonic stage of what would become our sun. This was no gentle process. It was a turbulent, chaotic environment where particles slammed into one another from all directions. As the protostar grew, it pulled in more material, its gravity intensifying. But the collapsing cloud wasn't a perfect sphere. It had its own angular momentum, a kind of cosmic spin inherited from the random motions of its particles. While particles approached the protostar from all angles, their collisions canceled out much of their momentum. Imagine a frenetic dance where dancers bump into each other, neutralizing their movements until only one dominant direction remains. This process flattened the chaotic cloud into a spinning disc-shaped structure known as a protoplanetary disk. This disk, swirling in a single plane, set the stage for the planets we know today. The protoplanetary disk was a game changer. As material continued to fall toward the protostar, the angle of these impacts caused the young sun to spin in the same direction as the disk. Over time, less material fell into the protostar, and more began to orbit it, clumping together within the disk. These clumps, driven by gravity, grew larger, forming planetesimals, small, rocky bodies that were the building blocks of planets. Some clumps grew massive enough to become planets, while others, around gas giants like Jupiter and Saturn, formed moons. This wasn't a unique phenomenon confined to our sun. The same process occurred around the planets themselves. Gas giants like Jupiter, Saturn, Uranus, and Neptune developed their own miniature disks of gas and dust, mirroring the protoplanetary disk. Within these disks, regular moons formed, orbiting in the same plane as their parent planet's rotation and in the same direction. Saturn's iconic rings are a stunning example of this process in action, orbiting in a plane aligned with the planet's equator, moving in perfect synchrony with its moons. The evidence is clear. This flattening into a single orbital plane is a universal feature of rotating systems in space. But how can we visualize this complex process? Imagine a stretchy sheet of fabric representing space-time with a heavy ball in the center acting as the protostar. If you roll smaller balls around it in different directions, they'll collide, canceling out their momentum until only those moving in the same direction remain. This is a simplified two-dimensional analogy, but in the three-dimensional reality of space, particles approached from all directions, colliding and aligning until a single dominant plane emerged. The result? A beautifully organized protoplanetary disk that gave birth to our solar system's planets, all orbiting in the same direction on a nearly flat plane. This process of flattening isn't just a relic of our solar system's past, it's observable today. Take Saturn's rings, a breathtaking example of a disk in action. During its 13-year mission, NASA's Cassini spacecraft captured images of tiny moonlets forming within Saturn's rings as particles clumped together due to gravitational interactions. Some of these moonlets disintegrated, while others persisted, potentially destined to become shepherd moons that carve paths through the rings. This ongoing process mirrors the early days days of our solar system, where material in the protoplanetary disk coalesced into planets and moons. Beyond our solar system, astronomers have observed similar disks around other stars. Using powerful telescopes like the Atacama Large Millimeter Submillimeter Array ALMA, scientists have captured images of protoplanetary disks around young stars, showing gaps and rings where planets are forming. These observations confirm that the process that shaped our solar system is a common feature of star formation across the universe. Even galaxies exhibit this flattening tendency, with stars and gas clouds orbiting in a plane around a central supermassive black hole, a testament to the power of angular momentum and collisions in creating order from chaos. While the solar system's orbital plane is remarkably flat, it's not perfectly so. Planets like Mercury and Jupiter have orbits tilted by a few degrees relative to the ecliptic, the plane defined by Earth's orbit around the Sun. These slight variations hint at the chaotic origins of the solar system, where gravitational interactions and collisions nudge some planets off the ideal plane. Dwarf planets like Pluto, with its highly inclined orbit of about 17 degrees, further illustrate these deviations, shaped by interactions in the distant Kuiper Belt. Despite these variations, the overall pattern is undeniable. The planets, moons, and rings of our solar system are aligned in a way that speaks to a shared origin. This alignment is a form of emergent structure through self-organization, a phenomenon where random, chaotic processes give rise to complex, orderly systems. Hurricanes, snowflakes, and even the formation of galaxies are other examples of this principle at work. In the case of our solar system, the protoplanetary disk transformed a turbulent cloud into a harmonious system of orbiting bodies, a cosmic masterpiece sculpted by the laws of physics. The early solar system was a violent place, characterized by relentless collisions that played a critical role in shaping its structure. As planetesimals and protoplanets formed within the protoplanetary disk, they didn't just peacefully coalesce, they slammed into each other with tremendous force. These collisions were not mere accidents, but pivotal events that determined the final architecture of the solar system. Larger bodies grew by accreting smaller ones, while some collisions were so catastrophic that they shattered planetesimals, creating debris that either fell into the sun, was ejected from the system, or became part of the asteroid belt and Kuiper belt. This period, known as the Late Heavy Bombardment, occurring roughly 4.1 to 3.8 billion years ago, left its mark on every planet and moon, as evidenced by the countless craters on bodies like the Moon, Mercury, and Mars. These collisions also influenced the orbital plane's stability. As objects collided, their angular momentum was redistributed, reinforcing the dominant direction of the protoplanetary disk while dampening deviations. This process helped refine the flatness of the orbital plane, as rogue bodies with highly inclined or eccentric orbits were either absorbed by larger planets or flung out of the system. The scars of this chaotic era are still visible today, particularly on airless bodies like the Moon, where ancient craters preserve a record of this violent past. By studying these craters, scientists estimate that the rate of impacts has decreased significantly over time, as the solar system settled into its current, relatively stable configuration. This transition from chaos to order is a hallmark of self-organizing systems, where the relentless interplay of gravity and collisions crafted the serene orbital plane we observe today. While the protoplanetary disk set the stage for the solar system's flat orbital plane, external forces from neighboring stars and the broader galaxy also played a subtle but significant role. As our sun formed within a stellar nursery, it was surrounded by other young stars, each exerting gravitational influence. These interactions could have perturbed the early solar system, introducing slight tilts or eccentricities in planetary orbits. For instance, a close encounter with another star could have tugged at the outer edges of the protoplanetary disk, affecting the orbits of distant objects like those in the Kuiper Belt or Oort cloud. Such encounters are thought to be responsible for the highly inclined orbits of some dwarf planets and the elongated paths of long-period comets. Today, the sun's motion through the Milky Way continues to shape the solar system's boundaries. As it orbits the galactic center at over 800,000 kilometers per hour, the sun plows through the interstellar medium, creating a bow shock where its solar wind meets interstellar gas. This interaction distorts the heliosphere, the bubble of solar influence, into an asymmetrical shape with a trailing tail stretching behind. The gravitational pull of nearby stars, like the Alpha Centauri system, further defines the sun's Hill sphere, limiting the stable orbits of distant objects. These galactic forces remind us that our solar system is not an isolated entity, but part of a dynamic cosmic neighborhood where external influences subtly sculpt its structure over billions of years. The legacy of the protoplanetary disk extends far beyond the formation of our solar system. It provides a blueprint for understanding planetary systems across the universe. Modern astronomy has revealed thousands of exoplanets orbiting other stars, many of which reside in systems with similar flattened orbital planes. Observations from missions like NASA's Kepler and TESS, Transiting Exoplanet Survey Satellite, show that multi-planet systems often have tightly aligned orbits, suggesting that protoplanetary disks are a universal feature of star formation. These discoveries validate the processes observed in our own solar system, where angular momentum and collisions conspire to create orderly systems from chaotic beginnings. Closer to home, the study of our solar system's minor bodies, asteroids, comets, and dwarf planets offers further clues about the protoplanetary disk's influence. For example, the Kuiper Belt, a region beyond Neptune, contains objects like Pluto, Haumea, and Makemake, whose orbits are generally aligned with the ecliptic, but show variations due to gravitational interactions over billions of years. Similarly, the Oort cloud, a hypothetical spherical shell of icy bodies, represents the remnants of the protoplanetary disk's outer edges, scattered by gravitational perturbations. By studying these regions, scientists piece together the solar system's early history, confirming that the flat orbital plane is not just a quirk, but a fundamental outcome of cosmic evolution. This connection between past and present, from our solar system to distant exoplanets, underscores the universal principles governing the cosmos, inviting us to marvel at the intricate dance of creation. The idea of a planet becoming a star might sound like science fiction, but it's a question worth exploring. Could Jupiter, our solar system's largest planet, have become a star if things had gone differently? To answer this, we need to dive back into the stellar nursery where our sun was born. Within the molecular cloud, multiple clumps of gas and dust were collapsing to form stars. Some clumps grew massive enough to ignite nuclear fusion, becoming main sequence stars like our sun, which accounts for 99.8% of the solar system's mass. Others, too small to sustain fusion, became brown dwarfs, objects often called failed stars because they lack the mass to shine brightly. Jupiter, despite its impressive size, is not a brown dwarf. With a mass about 0.1% of the solar system's total, it formed within the sun's protoplanetary disk, not independently in the molecular cloud. As the sun greedily consumed most of the available material, Jupiter was left with too little mass to ignite fusion, even the limited fusion that powers brown dwarfs. In this sense, Jupiter is a failed star, only in the same way all planets are. It formed in a disk where the sun dominated, leaving insufficient material for another star to form. However, in other star systems, binary or multiple star systems are common, where two or more stars form close together and orbit each other. If our sun had formed alongside another star, or if Jupiter had accumulated significantly more mass, the story might have been different. But as it stands, Jupiter's fate was sealed by its position in the sun's disk, making it a gas giant rather than a star. This dynamic highlights the delicate balance of mass and timing in the formation of celestial bodies. How far does our solar system extend? Is it to Pluto's orbit, the Kuiper Belt, or beyond? The Voyager spacecraft, launched in 1977, provide a clue. As of July 26, 2025, Voyager 1 and Voyager 2 are still operational, powered by radioisotope thermoelectric generators, though their energy is dwindling. These probes have crossed the heliopause, the boundary where the sun's solar wind is overtaken by interstellar wind, Voyager 1 in 2012 and Voyager 2 in 2018. This milestone led some to claim they had left the solar system, but the reality is more complex. The heliopause, a bubbly, asymmetrical boundary shaped by the sun's motion through the interstellar medium at over 800,000 kilometers per hour, marks the edge of the sun's magnetic influence, not its gravitational reach. The true boundary of the solar system is the Hill sphere, the region where the sun's gravity dominates over nearby stars. This sphere isn't perfectly spherical, it's distorted by the uneven distribution of neighboring stars, like the Alpha Centauri system, 4.37 light-years away, and Barnard's star, 6 light-years away. The sun's Hill sphere extends roughly 1 to 2 light-years, encompassing the Oort cloud, a sparse region of icy bodies believed to be the source of long-period comets. The Oort cloud, stretching from about 2,000 to 100,000 astronomical units, AU, is mind-bogglingly vast. Voyager 1, traveling at about 61,000 kilometers per hour, will take roughly 300 years to reach its inner inner edge and up to 30,000 years to pass through it. Objects at the outer edge of the Hill sphere orbit precariously, vulnerable to perturbations from passing stars. This defines the practical limit of the solar system, though theoretically, a solar system could extend much farther under unique conditions. What's the largest a solar system could be? To explore this, consider a star with no nearby competitors, isolated in the vastness of space. The most massive known star, R13601, weighs about 300 solar masses and resides in a dense cluster where its Hill sphere is limited by neighboring stars. But imagine such a star alone, with no gravitational rivals for light years. Its Hill sphere could span hundreds or even thousands of light years, comparable to a small galaxy. In an extreme scenario, with only two objects in the universe, a massive star and a single orbiting body, the second object could be billions of light years away and still be gravitationally bound, as gravity's influence never truly vanishes with distance. In our universe, such extreme isolation is unlikely, as stars form in clusters and galaxies interact. But this thought experiment underscores the incredible scale of gravitational influence. Our solar system, with its Hill sphere extending 1 to 2 light years, is vast but modest compared to these theoretical extremes. To grasp the solar system's scale, imagine the sun as a grain of sand, just 1 millimeter in diameter. At this scale, Mercury is 4 centimeters away, Venus 8 centimeters, Earth 10 centimeters, and Mars 16 centimeters. The asteroid belt home to dwarf planet Ceres starts at about 30 centimeters. Jupiter, the largest planet, is 56 centimeters away, followed by Saturn at 1.03 meters, Uranus at 2.06 meters, and Neptune at 3.24 meters. Pluto in the Kuiper belt lies 4.22 meters away, but the nearest star, Alpha Centauri, is a staggering 30 kilometers away, a distance that highlights the immense isolation of our solar system in the cosmic neighborhood. Now, scale up the sun to the size of a soccer ball, about 11 inches across. Mercury is now 38 feet away, Venus 70 feet, Earth 93 feet, and Mars 141 feet. Ceres in the asteroid belt is 277 feet away, while Jupiter looms at 484 feet. Saturn is 939 feet, Uranus 1,890 feet, and Neptune 2,963 feet. The Kuiper belt extends from 3,000 to 5,000 feet, with Pluto at about 3,900 feet. Dwarf planets like Haumea and Makemake are around 4,300 to 4,500 feet, and Eris, one of the farthest known objects, is 6,800 feet away. The Oort cloud's inner edge is a mind-blowing 1.2 miles away, with its outer edge potentially 60 miles distant. This scale model underscores the solar system's vastness, with distances that challenge our everyday perceptions. Let's debunk some common myths about our solar system, revealing the truth behind these cosmic misunderstandings. The solar system formed during the universe is about 13.8 billion years old, born in the Big Bang, but our solar system is much younger, forming about 4.6 billion years ago from the collapse of a molecular cloud. Most of that cloud became the sun, with the rest forming planets, moons, and other bodies. Comets always have tails. Comets only develop tails in a coma, a fuzzy cloud of gas and dust when they approach the sun. The sun's heat vaporizes their icy surfaces, creating tails that always point away from the sun. Far from the sun, comets are dark, inert objects. The sun accounts for a small part of the solar system's mass. The sun dominates, holding 99.8% of the solar system's mass. Jupiter and other gas giants make up most of the rest, with Earth and smaller bodies contributing a tiny fraction. Mercury is the hottest planet. Despite being closest to the sun, Mercury isn't the hottest. Venus, with its thick atmosphere trapping heat, reaches average temperatures of 462 degrees Celsius, compared to Mercury's maximum of 426 degrees Celsius. Mercury is tidally locked to the sun. Once thought to be tidally locked like the moon to Earth, Mercury actually has a 3-to-2 spin-orbit resonance, rotating 3 times for every 2 orbits around the sun. Asteroids in the asteroid belt are close together. Hollywood portrays the asteroid belt as a crowded obstacle course, but asteroids are about 1 million miles apart on average, with a total mass just 4% of the moon's. Comets come from outside the solar system. Comets originate within the solar system from the Kuiper Belt, short-period comets, or the Oort cloud, long-period comets, not from interstellar space. Saturn is the only planet with rings. All gas giants, Jupiter, Saturn, Uranus, and Neptune, have rings, though Saturn's are the most prominent. Jupiter's faint 26. The solar system formed during the Big Bang. The universe is about 13.8 billion years old, born in the Big Bang, but our solar system is much younger, forming about 4.6 billion years ago from the collapse of a molecular cloud. Most of that cloud became the sun, with the rest forming planets, moons, and other bodies. Comets always have tails. Comets only develop tails and a coma, a fuzzy cloud of gas and dust when they approach the sun. The sun's heat vaporizes their icy surfaces, creating tails that always point away from the sun. Far from the sun, comets are dark, inert objects. The sun accounts for a small part of the solar system's mass. The sun dominates, holding 99.8% of the solar system's mass. Jupiter and other gas giants make up most of the rest, with Earth and smaller bodies contributing a tiny fraction. Mercury is the hottest planet. Despite being closest to the sun, Mercury isn't the hottest. Venus, with its thick atmosphere trapping heat, reaches average temperatures of 462 degrees Celsius compared to Mercury's maximum of 426 degrees Celsius. Mercury is tidally locked to the sun. Once thought to be tidally locked like the moon to Earth, Mercury actually has a 3-to-2 spin-orbit resonance, rotating 3 times for every 2 orbits around the sun. Asteroids in the asteroid belt are close together. Hollywood portrays the asteroid belt as a crowded obstacle course, but asteroids are about 1 million miles apart on average, with a total mass just 4% of the moon's. Comets come from outside the solar system. Comets originate within the solar system from the Kuiper Belt, short-period comets, or the Oort cloud, long-period comets, not from interstellar space. Saturn is the only planet with rings. All gas giants, Jupiter, Saturn, Uranus, and Neptune, have rings, though Saturn's are the most prominent. Jupiter's faint rings and Uranus's 13 rings are harder to observe. Pluto is the farthest object in the solar system. Pluto lies in the Kuiper Belt, but the Oort cloud extends far beyond. Dwarf planets like Eris, up to 97 astronomical units, and Sedna, up to 937 astronomical units, are much farther. The sun is a burning ball of fire. The sun glows due to nuclear fusion in its core, not chemical burning, at 15 million degrees Celsius in its core and 5,500 degrees Celsius at its surface. The story of why all the planets orbit on the same plane is a testament to the universe's ability to create order from chaos. From the turbulent collapse of a molecular cloud to the elegant dance of planets, moons, and rings, the solar system's structure is a product of angular momentum, collisions, and gravity working in harmony. This process isn't unique to our corner of the cosmos. It's a universal principle observed in distant star systems and galaxies. Whether pondering Jupiter's unrealized stellar ambitions, the vast reach of the sun's gravitational influence, or the mind-boggling scale of our solar system, one thing is clear: the universe is a place of endless wonder, inviting us to explore, question, and marvel at its mysteries. Keep watching, keep wondering, and let the cosmos continue to inspire you.